Hey everybody, Mrs. Cat here to talk about Lab 1, Mass and Change. At this point, you have either watched videos on all 6 parts of the lab or done the lab in person. You have done some data collection and analysis. You've drawn particle diagrams for all parts and done a reflection question. What I'm going to do is walk through what really is happening, what we should see in our particle diagrams. Going to make sure that we are getting the correct info out of our mass data, and then drawing some conclusions from things that you saw, observed, and things that we see in our particle diagram. So that's kind of how my page is set up. Before we get started, just want to make sure that you understood where I'm going with this. So part 1, mass of steel wool. Steel wool is our only substance. So when we draw our particle diagram, that's the only thing that we're going to show. I'm going to start with my steel wool particles. So I'm going to use gray, and let's go with like 6 dots here. I know that my mass before was 8.17 grams. I also want to take time now to go ahead and make a little key. That's what this space is going to be for, that equals steel wool. Okay. Mass after the change, which was taking the piece of steel wool, pulling it apart, so it was taking up more space. That final mass was also 8.17 grams. Mass stayed the same, so that's one of the things we want to make sure that we show. Now, one of the things that we need to make sure that we think about as far as our particle diagram is concerned, if the mass stays the same, that means that the number of particles is going to stay the same. I'm going to use a little symbol here. This is 3 dots that make a triangle. This symbol right here means therefore, and I'm going to use this pretty frequently. Okay, so when you see that 3 dots in a triangle, that means therefore. Okay, so the mass stays the same, therefore the number of particles stays the same. Now, the thing that does change is the steel wool itself takes up more space. So what we want to show in our particle diagram is that our particles are the same in number, but they're further apart to represent that it's taking up more space. So we're going to write that down. Further apart. Okay. We have 6 particles. I'm going to draw another set of 6 particles. Same color, same size, but this time I'm going to draw them further apart. Okay. Again, mass before, mass after is the same, so we can go ahead and show that our change in mass, that is final minus initial, is 0 grams. Okay. One of the things we also want to consider when we're thinking about each of these changes is whether or not a physical or chemical change took place. Now, in this particular part, we have steel wool before and steel wool after. So this is going to be a physical change. And I'm going to underline that to make this stick out as part of our conclusions. And this is because we have no new substance that's formed in our change. Same thing, steel wool, just a difference in how much space it takes up because of the particles being spread out more. Okay, that's part 1. Let's take a look at part 2. Okay, part 2 is the mass of ice and water. I want to go ahead and fill in my data first for the before. The before, the mass of the beaker with the water and the ice in it was 30.63 grams. Okay, now a couple of things I want to think about as we are getting started with this. First thing, ice is solid water. So we only have one substance here. Again, I'm going to use my 3 dots for therefore. Only water, I'm going to use H2O, is present. And this is both before and after. Okay, so I'm going to represent my water particles with a blue dot or blue circle. And this is going to equal water. Now, what we want to show here is that the particles of water that are representing water in its liquid state and water in its solid state of ice are the same particles, but they need to be arranged differently. So let's make a note of that here. Water particles are the same, but arranged differently. For liquid and solid. Okay. In the particle diagram, what I'm going to draw here is, I'm going to make this kind of simple here. So let's pretend like my whole box is the beaker, right? Now, hopefully you noticed, or maybe you know from your own personal experience, that ice actually floats in water. It's a little bit less dense. So I'm going to draw my ice cubes at the top. Now I'm going to put my ice particles of water a little closer together. Okay. And then because liquid water flows, I want to put those particles a little bit further apart. Now, I've got 6 ice particles. I've got 6 water particles. I want to go ahead and write down my final mass, which was 30.60 grams. So if we take final minus initial, we're going to see that we lose 0.03 grams from the initial to the final mass. Now, this actually isn't showing a loss of mass. Okay, this shows that the mass is really, really close. Okay? The difference here is really just because of the calibration of the balance that was used. Okay? This is really close, and this just comes from the fact that the balance was reset and re-zeroed in between the time when the ice was put in and was solid and after it melted. So what we want to show here is that there is no change in mass. So we're going to have the same number of particles. The difference is after they're all in the liquid form. Okay, so my after picture, I'm going to draw another little squiggle. That's really not necessary, but I just kind of like it here. Particles. Again, I had 6 ice, 6 water for a total of 12 water particles. So I need to have 12 spaced out to represent the fact that they're in the liquid form. So 5, 6, 7, 8, 9, 10, 11, 12. Okay. That represents what we have going on here. Now, again, water before, water after. This is going to show that we have a physical change. Okay. Still water before and after. Okay. Moving right along to part 3, mass of a precipitate. This time we have 2 different substances. Okay, we have solution A and solution B. It doesn't really matter for what our purposes are here, what those substances actually are. We're just going to label them as solution A. And then let's go with, like, I don't know, orange for solution B. Now, these were actually calcium chloride and sodium carbonate solutions. What we want to show in our pictures is what's going on. Okay, let's do our observations and conclusions first before we get into particle diagrams. These were both clear solutions before. And then they formed a cloudy mixture when mixed. Yeah, that sounds silly. Let's just say that they were cloudy when mixed. Okay. Because they went from clear and clear into cloudy, this is evidence that a new substance formed. Which means this is a chemical change. Okay, let's dive into our mass data and our particle diagrams. Mass data before our initial is 19.42 grams. After 19.45 grams. So we have a slight increase. This is going to be a change of 0.03 grams. Again, just like in part 2, even though we have this tiny increase, this is really about a difference in the calibration of the balance between when the before and after parts were measured. This really is going to show that we have no change in mass. No change in mass. Therefore, we have the same number of particles. Okay, I'm going to split my boxes for before and after into 2 because we had 2 separate vials. Okay, let's see here. Let's go with solution A. I'm going to put like 6 particles in for before. Let's do the same thing. 1, 2, 3, 4, 5, 6 for solution B. Okay, you're mixing them together, so we're going to end up with 1 empty vial and then a separate vial with our new cloudy mixture. Because we have a new substance formed and we know it came from solution A and solution B, we're going to show that the particles are connected to one another to form this new substance. That way we can still show the same number of particles, a total of 12 in this case, instead of having 1 particle representing our new solution, okay, or our new substance. So I'm going to leave this first one blank. 1, 2, 3, 4, 5, 6. There's our solution B. And then again, I said I want to attach these or connect these, and I'm just going to kind of do it randomly. It doesn't really matter. Okay, as long as they're touching to show that this is a new substance made of A and B. So let's clarify this. New substance shown by connecting particles for A and B. Okay, that'll sum up part 3 for us.